Hello students. In the previous session we were discussing about different compiler techniques used for the process of reducing or increasing the performance of insertion level parallelism. So the method that we are focusing now is the various compiler techniques for improving the insertion level parallelism. So we have already discussed about two mechanisms. One is the loop unrolling mechanism, and second one is the scheduling applied to the unrolled loops. So based on these two, we can actually reduce the number of statements present in the set of instructions, and because of that we can reduce the total time taken for the completion of the entire task. Now we will look at one more compiler technique, that is called as advanced branch prediction. Second compiler technique that is used to improve the performance of the insertion level parallelism is to use advanced branch prediction. So what is this branch prediction? So what is the aim of predicting the branch, or how a branch will be working, or how the branch will be behaving in the future? If we have some such prediction, we can actually reduce the branch cost that will be created, or the more cost if we are having some more number of branches available, and because of these branches there will be more cost that happens within the given set of instructions available in a program. So if you reduce and if you try to predict the branches, how the branch will be behaving, and accordingly if we perform the sequence of execution, we can actually reduce the branch cost also. So by reducing the branch cost, we can improve the parallelism. So as we have already mentioned, loop unrolling is one way to reduce the number of branch hazards. So loop unrolling, so in our previous example you have already seen that if you are having some 100 iterations available, we can do some modification on that by doing loop unrolling. Actually what we are getting, we are actually reducing the number of branches available. If the number of branches being reduced, it will automatically reduce the hazards that are created due to the branches or controls. So now we can also reduce the performance losses of branches by predicting how the branches will behave. Okay, so if a branch is available within a set of instructions, and if you know how that branch will be behaving, whether the branch will be happening or whether the branch will not be happening, accordingly if it controls the sequence of execution, we can actually improve the performance of the system. So if we cannot predict the performance or the behavior of a branch, sometimes what happens is, if an instruction is like if A is an instruction, then comes B, then comes C. Assume that we are having some instructions like this, and C is a branch instruction. C is a branch instruction, for example. So A will be executed in order, then B will be executed, then C is a branch statement. Whether so there will be some condition, and sometimes if that condition is true, it will enter into the loop or that branch statement, like it will enter into the C. Then we'll be having another statement. So sometimes if it is not entering into this particular branch, it will go to this particular area. Okay, so normally the instructions are written like first it is written A, then it is written B, then it is written C, then it is written the body of this C, then it is written D. So what happens is, if the instructions are written in this order, the instruction level parallelism will be happening in the overlapping order, that is in the form of pipelining. Means according to sequence of insertion, the insertions will be executed in this particular order. So A will be performing here, then B, then C, then the body of C, then we are having D. This is the actual order. But like for example, if it is not entering into this particular branch, what will happen? It will directly go to D. But what happens in between is some portion of these instructions were also started its execution within this pipeline. So that may create some problem, because actually the branch is not being taken. So if it is going into the body of this particular branch statement, or if it is going into the loop into some other portion, then there will be a confusion. So we need to do some additional operation to undo all these operations that already happened with the set of insertions that are available as part of the branch. So in order to avoid this, we are actually doing the process called as branch prediction. As the number of insertions has increased, the importance of more accurate branch prediction has also been grown. So if the program consists of more number of instructions, automatically we will be having more number of branches also available. Even with a single loop itself, we are having a number of branches available. So if we apply some prediction on this particular loop that consists of a number of branches, we can reduce the total time taken for the completion of that particular loop by predicting the behavior of a branch operation. So we will see in detail about how we can do this prediction. So we are actually going to discuss about correlating branch predictors. So one of the major type of prediction algorithm that we are using is correlating branch prediction. So before moving into that, we will see one basic predictor that is called as 2-bit predictor, which was very commonly used earlier, and it is using the recent behavior of a single branch. The recent behavior of a single branch to predict the future behavior of that particular branch. So for example, if you are having a branch B1, then we are having a branch B2 available. Now if we want to evaluate the execution of branch B2, it will just look into the behavior of the same branch before. Okay, so this is not B1, this is actually B2 itself. We are having the same. For example, in a loop we will be repeating the same branch again and again. So the branch will look into the behavior of its previous branch statement for the same single branch itself, how B2 behaved earlier. Accordingly, it will predict. So automatically what we are guessing is B2 will perform as it was in the previous branch statement. So we are assuming that B2 will perform in the same way as it is done in the previous situation. Okay, if it is being repeated 100 times, so first time it is behaving in one way, that means whether it will be entering into the body of branching statement or it will be going out of the branching statement. So if it is means previous branch is going inside the body of that particular branch, we are predicting like B2 in the next chance also it will enter into the body of that particular branch. in the reverse way, if we say if B2 is not entering into the body, that means it is again going out of that particular branch body. Now B2 in the next chance also we will predict like B2 will also go out of the body of that particular branch. In that way we will predict the future behavior of a single branch. So that mechanism, that is called as a 2-bit predictor mechanism. So it will just look into the recent behavior of the same single branch to predict the future behavior of that particular branch. Okay, so for example, for I equal to 0 to 100, for I equal to 0, what will happen? Then for I equal to 1, we are predicting that the same thing will happen. For I equal to 2, we are predicting that the same thing will be happening. For I equal to 3, we will predict that the same thing will be happening. So accordingly, the pipeline will be executed in that particular order. So here we are actually predicting. So what we are getting is we will be making the flow of execution of different instruction in a proper pipeline order. So it is a very basic mechanism that is called as 2-bit predictor. It may be possible to improve the prediction accuracy if you also look at the recent behavior of other branches rather than just the branch we are trying to predict. So this 2-bit predictor is always looking at the behavior of the same branch. So if B2 to be executed once again, it will just look at the behavior of same branch in the previous situation. Then we will take what happened there and it will continue. But it is always better to use the recent behavior of other branches also to make the prediction on the behavior of a new branch. That is also possible. So we will see in detail about that mechanism, which is actually called as correlating branch predictors. Consider, we'll see one example. You can see a set of branch statements here. So it's a very simple code. If A is equal to 2, if it is true, it will enter into the body of if we are assigning A is equal to 0. If A is equal to 2, A equal to 0. A simple condition, if it is true, we are assigning 0 to this particular variable. Then if BB is equal to 2, we are assigning 0 to BB. The same type of operation happens here also. Then after that, if A not equal to B, if A not equal to B, if these two are not equal to B, we are having some other body. Okay, so what is happening here? If A equal to 2, it will enter into the body of that particular branch. That means sequential operation. If A equal to 2, this is the first operation, then it will execute the second operation if it is true. Then it will execute third operation if BB equal to 2. If it is true, it will execute the next operation. Then it will go for the next operation. So this is the sequential order. So if you form pipeline, so first this operation will start with insertion fetch, insertion decode. Then similarly, then A equal to 0. Then if BB equal to 2, then BB equal to 0. Then if A not equal to B, like that it will be going in a pipeline order. If it is happening in the order itself, but it is not always possible, because if A not equal to 2, what will happen is it will not enter here. There will be a branching that happens from this location to this location. It is a taken branch, means this branch is being taken. If A equal to 2, it will enter into the sequential statement. If A not equal to 2, it will go to the branch. It will go into a separate statement. Then again, if BB not equal to 2, what will happen? It will not enter into the sequential statement. It will again go to the next branch. It is also a taken branch. If A is not equal to 2 and BB is not equal to 2, then it will go to the third statement, third branching statement, that is if A not equal to B. So that situation, it will be entering into the sequential statement. So what I am trying to say is that the behavior of this branch is actually depending on the behavior of previous two branches that is already being executed before the execution of this particular branch. In the previous case, we were looking at the performance of the same branch for the previous situation, but now for deciding what happens with this particular branch, just look at some other branch behavior also. Okay, so if A equal to 2, B equal to 2, what will happen? This will be wrong, right? Then A not equal to 2, BB not equal to 2, this will be correct. These they are not equal, so it will enter into this particular body. So this behavior of this branch will be based on the behavior of other two branches also. That is why it is called as correlating branches, and the prediction is done based on these correlating branch operations. So this branch is not only depending on the behavior of its own, it also depends on the behavior of its correlating previous branch operations also. Okay, so just for giving some more understanding to the same correlating branch predictor, we will convert this code into a MIPS instruction set format. Then we will give some explanation on the same thing. So just remember, if A equal to 2, A equal to 0. If BB equal to 2, BB equal to 0. If A not equal to B, then some operations as part of that particular condition. Now this is the corresponding MIPS code for the previous example. Now A is replaced with R1 register and BB is replaced with R2 register. It is given in a different format. It is actually giving the same result as the previous example. So what we are doing is double add immediate unsigned R3 comma R1 minus 2. What is R1? A minus 2. A minus 2. A minus 2. We are doing A minus 2. For example, if A is 2, 2 minus 2 will be getting 0. Okay, so in the previous case we can see what happens here. Here it is A equal to 2. So if we assign A as 2, 2 minus 2 is equal to 0. That will actually happen. Okay, so for getting A as 2, we need to find out A minus 2. That means 2 minus 2 is equal to 0. Okay, so that way we are actually doing the same operation. So that A minus 2, then we are getting that value into R3. So A will be giving a minus 2 operation and the result is stored in R3. Result is stored in R3. Then we are checking R3 branch on non equal to 0. If it is not equal to 0, go to L1. If it is not equal to 0, go to L1. It will go to a branch that is L1 if it is not equal to 0. This is branch B1 when A not equal to 2. Okay, not equal to 0 means it is not equal to 2. Otherwise, what will happen? It will add 0. If it is equal to 0 into R1, 0 comma 0 will be added. 0 plus 0, that is 0 will be added to the variable A. So this is actually the same operation that is given in the previous example in MIPS format. Then if it is not equal to 2, what will happen? It will go to L1 again it will do R2 minus R2, I mean R2 minus 2, that is BB minus 2, like AA minus 2, here it will be BB minus 2. It will do the same thing, branch on non equal to 0, R3, that is the result of this one. If it is not equal to 2, L2 go to L2. Okay, otherwise what will happen? It will add 0 plus 0 to R2, it will become 0. Same operation for the previous case, A equal to 0 if it is equal to 0, BB equal to 0 if it is equal to 0, if this branch operation is equal to 0. Okay, now in the third stage what is happening is it is doing a subtraction operation between R1 minus R2, that means AA minus BB. If it is equal to 0, it will go to branch 3, that is the next branch, it is not mentioned here. Okay, so the decision on this branch B3 is depending on both branch B2 and B1. That is the only thing I just want to mention here. It's not a very difficult thing. Here, for predicting the performance of a branch operation, it is considering the behavior of some other branches also executed before the current branch. Okay, once again, in order to predict the behavior of a particular branch, it will also look at the behavior of some other branches which was executed before the current branch operation. Okay, so we'll give some more explanation on this. The behavior of branch B3 is correlated with the behavior of branches B1 and B2. That's what I was trying to say. The behavior of branch B3 is correlated with the behavior of B1 and B2. Now, if the branches B1 and B2 are both not taken, if the branches B1 and B2 are not taken, that means if it is not going to branch, it is not taken. If the branch is not taken, if it is not moving towards that particular branch, then B3 will be taken. So we are actually predicting B3 will be taken. As per our previous example, then B3 will be taken. If it is the opposite thing, if B1 and B2 are taken, B3 will be not taken. Okay, since it is very clear that A and B are clearly equal. Okay, so that depends. The behavior of B3 will be depending on the behavior of B1 and B2. That is the only thing that was explained in the previous example. So branch predictors that use the behavior of, so this is the major point, branch predictors. So we are considering a compiler technique for improving insertion level parallelism. For that we are using branch predictors. First predictor is 2-bit predictor. Second predictor is correlating branch predictor. So the branch predictor that use the behavior of other branches to make a prediction are called correlating predictors. It is also called as 2-level predictors. So previous one was 2-bit predictor was only 1-level predictor. It looks at the behavior of the same branch itself in the previous situation, but correlating predictors, it looks at the behavior of other branches to make the conclusion on the current branch. These type of predictors are called as correlating predictors. Existing correlating predictors add information about the behavior of the most recent branches to decide how to predict a given branch. Same thing only. Now we can call this predictor as For example, it will be notated in this particular way. For example, a 1, 2, a 1, 2 predictor uses, now this is the name given for the correlating predictor, that is 1, 2 predictor uses the behavior of the last branch, to choose from among the pair of 2-bit branch predictors on predicting a particular branch. So in this situation, 1, 2 predictor, it will utilize, or it will choose, or it will take the behavior of the last branch to choose from among the pair of 2-bit branch predictors on predicting a particular branch. That is called as 1, 2 predictor. And in general, we can call it like an MN predictor that uses the behavior of the last M branch. That's what we were mentioning in the previous example. It will use the behavior of last M branch to choose from 2m branch predictors for different branch predictors, each of which has an n-bit predictor for a single branch. For each branch, it will be having its own n-bit predictor. Along with that, it will take the behavior of the last M branch also. So this is the general notation, MN predictor, or for example 1, 2 predictor, 1, 3 predictor, 2, 2 predictor, etc., etc. MN predictor that uses the behavior of the last M branch to choose from 2m branch predictors, each of which has an n predictor for a single branch. The correlating branch predictor yields higher prediction rates than a normal 2-bit scheme. Okay, so it can do a better prediction than a single bit scheme or a 2-bit scheme, and also requires only a trivial amount of additional hardware. So for doing this additional prediction, for getting the details of the other two, so for predicting this branch, I need to get the information about the just previous and its previous branch. We need to have some additional hardware for processing this operation. We need to have some small amount of additional hardware. So only with the support of that hardware, so we need to have some modification added to the architecture so that we can identify the behavior of a new branch based on the existing previous branches. So if we predict the behavior in that way, we can actually make a proper flow of pipeline, and we can increase the speed of the entire set of instructions available in the system. Then another mechanism based on the same 2-bit predictor and MN predictor, that is correlating predictor, we are using another general category of predictor that is called as tournament predictors. It is actually a combination of local and global predictors. Local predictors means the prediction based on the local branches only. Global predictors means for this local we are also considering the global or other branch performance also, as it was given in the previous example. So the primary motivation for correlating branch predictors came from the observation that the 2-bit predictor uses only the local information, and it failed on some important branches. So that is based on the experiment, or based on the experience. They have identified that only getting the information on the local branches have already failed, or they are not performing well for certain branches. So what they are doing is they are trying to add some global information also. That situation, the performance will be slightly improved. So tournament predictors take this insight to the next level by using multiple predictors. One predictor based on the local information, and the second one is based on the global information. So one based on global information and one based on local information, and combining them with a selector to predict the behavior of a given branch. So a tournament predictor uses the behavior of the performance of or the behavior of the local branch informations as well as the global branch informations also. Now we can achieve both better accuracy and also make use of very large number of prediction bits effectively when we are using the tournament predictors. It uses a 2-bit saturating counter per branch. So for each branch it uses a counter to choose among two different predictors based on which predictor was most effective in recent prediction. So we are keeping a predictor. So we are having some local information here. So we are having a local set of information here, and we are having a global set of information here. Local information and global information, and we are having a counter associated with these two. We are having some counter like C1 and C2, and we will take the information, and each time it will be incrementing the counter value into some number of times. For example, it is global information gets 5 and this is getting 3. For example, in this situation it will be predicting the branch based on the global information because it gets more score when compared to the local information. So that is why it is called as a tournament predictor. So in a tournament, two team will be playing, and whichever team gets more points will be the winner. So similarly, here we are having two team members. One is the informations from the global branches and the informations about the local branches, and whichever is getting more counter value will be selected, and based on that the prediction of the current branch will be executed. So that is why it is called as a tournament predictor. So whichever gets more points, more counter values, that prediction will be that was the most effective prediction that is considered for the current branch. Now the advantage of this scheme is to select the right predictor for a particular branch, because we are having a comparison between some set of local information as well as some set of global information, so that we will select the right predictor. So which will be a better predictor, a most close predictor for the current branch. Now a typical tournament predictor will select the global predictor almost 40% of the time, and less than 50% of the time for the most of the time the global predictor will take or giving more prediction. It is taken from the spec integer benchmark. For a particular benchmark, it is around 40% predictor is taken from the global predictor mechanism for spec integer benchmarks, and less than 15% of the time for the spec FP benchmark. So we have simply taken two benchmark, two spec benchmark, where we are applying this global predictor. For the spec integer benchmark, 40% of the time the global predictor was successful, and for spec FP benchmark 50% of the time it was less than 15% of the time it was a successful prediction for the spec FP benchmark. So what is tournament predictor? Tournament predictor gives a prediction on a branch based on the local information as well as global information, based on the higher prediction, based on the higher value that is received either from the local or global information, that prediction will be considered, and accordingly the branch will be acting in the near future. Okay, so that is the way how we are working on the tournament predictors. So this is another compiler technique that is used to improve the performance of insertion level parallelism. Now we will look at the one specific processor, that is Intel Core i7 processor, and how we will give some explanation on the branch predictor that is used in Intel Core i7 processor. Here it is based on earlier predictors used in Core Duo chip. It was so here it is following not any it is following earlier 2-bit mechanism and all predictor mechanism for the Core i7 system. It uses 2-level predictor. That's what I was mentioning here. The first level designed to meet the cycle constraints of predicting a branch every clock cycle. So it is trying to predict the performance of a branch on every clock cycle. So there will be a cycle constraints added in the first level, and in the second level it is used as a backup. In the second level predictor used as a backup for the prediction that we are getting for the current branch. Now each predictor combines 3 different predictors. In the case of Core i7, it uses 2-bit predictor, a global history predictor, and a loop exit predictor. So for different processor there will be different prediction mechanisms available. So just considering the performance of Core i7 in the case of branch prediction, it uses a 2-bit predictor, simple 2-bit predictor. It uses a global history predictor as in the case of tournament predictor, and it also uses a loop exit predictor, that is based on the exit condition, based on the loop exit condition, and based on that prediction it can actually identify or predict the behavior of a particular branch. So a loop exit predictor uses, so it is a new thing here, a loop exit predictor uses a counter to predict the exact number of taken branches for a branch that is treated as a loop branch. So a loop exit predictor uses a counter to predict the exact number of taken branches. So previous case we were considering about not taken branch. Sometimes it will be taken branch also, it is always taken, it is moving towards the branch, and sometimes if it is not taken means it is not moving towards the branch. So here it will take the counter to predict the exact number of taken branches for a branch that is treated as a loop branch. For a loop branch it will take the exact number of taken branches and its count, and based on that count the behavior of the current branch will also be decided. So this is only a case study given, that is the performance or the use of branch predictor compiler technique mechanism for improving the performance of insertion level parallelism in the case of a specific processor called as Intel Core i7. So today's session we have discussed about the compiler techniques called as branch prediction, different types of branch prediction, basic 2-bit prediction. Then we are having the other predictions like correlating branch prediction that uses MN predictor mechanism. Then we are having tournament predictor, and in Core i7 we are using a new predictor that is called as loop exit predictor also. So this is one of the this is a second mechanism that is used as compiler technique. First one was like loop unrolling and scheduling, where we can reduce the number of codes and we can increase the speed of the different instructions available. Then here for exclusively for branch we are applying these predictions, so because normally branch will be behaving in different way in different situations. So if you predict the behavior of that branch properly, we can assign the pipeline in the order according to the prediction, so that we will be getting a better pipeline architecture, and we can increase the speed of the insertions that are part of the currently executing system. So that's it for now. We will see some more details or some more mechanism that is used for improving the performance of insertion level parallelism in the next sessions. Thank you.